All right. Hello, everyone. Welcome to our ARSET training series, LiDAR Profiling Satellite Observations for Air Quality Applications. My name's Ed Nowottnick, and I'm a researcher at NASA Goddard Space Flight Center outside of Washington, D.C. So before we begin today's training, I'll say a few words about the ARSET program. The NASA Applied Remote Sensing Training, or ARSET program, provides cost-free training on the use of remote sensing observations, analysis methods, and tools. We provide training in several thematic areas: agriculture, climate and resilience, disasters, eco-conservation, and wildfires, health and air quality, and water resources. ARSET provides both online and in-person trainings. Our online trainings can be instructor-led, like today's training, or asynchronous and self-paced. Whether in person or online, all of our trainings are offered at no cost. We try to offer trainings in more than one language whenever we can, and our trainings only use no-cost and open-source software and data. It's worth noting that all NASA data are available at no cost, and we try to offer trainings at a range of levels so you can find training that fits your level of experience and need. Please visit the ARSET website, which I'll show at the end here, to learn more. Okay, so getting into an overview of what we'll be talking about today. Okay, so here I'm going to be providing a video on some of the capabilities that highlight LiDAR remote sensing. And here I'm going to cut to a loop of some of the surface observations that provide ground-based measurements of surface air quality. And you can see that they're pretty sparsely dispersed across the continental US in this case. These are all provided at the ground, and the advantage of LiDAR remote sensing is you get full column measurements that are vertically resolved that provide air quality measurements all the way up through the column of the measurement. So for today, we're going to be focusing on the following training learning objectives. And at the end of this training, we hope you'll be able to recognize the capabilities of LiDAR active remote sensing in measuring vertical profiles of aerosols and clouds for informing air quality applications, interpret information within LiDAR curtains to discern cloud phase, aerosol type, and aerosol plume altitude for a given scene, recognize the strengths and limitations of LiDAR observations, and find LiDAR images and data for a particular time period and location using NASA Earth data and mission websites. Prerequisites for this course are fundamentals of remote sensing. All right, so this is the training outline for our two-part training. Part one today on June 4th is Introduction to LiDAR Measurements and Missions. And next week on June 11th, we will be doing part two, interpreting LiDAR observations and accessing LiDAR data. Following the completion of part two, we will be handing out homework that hopefully captures all of the topics and skill sets we've covered in this training, and that'll be due on June 25th, and that homework will be posted on our training webpage. Following the completion of the sessions and the homework, we will be providing a certificate of completion to those who have completed everything. All right, so let's get into part one, LiDAR profile satellite observations for air quality applications. All right, so for part one, I'll be your trainer. Again, my name is Ed Nowottnick, and again, I'm a research physical scientist at NASA Goddard Space Flight Center. Okay, so the objectives for part one are to recognize the capabilities of LiDAR active remote sensing in measuring vertical profiles of aerosols and clouds for informing air quality applications, to recognize the strengths and limitations of LiDAR observations, and to identify past and current available LiDAR missions and their characteristics. So before we get started, we'll do a review of our prior knowledge. We're going to understand the differences between active and passive remote sensing. Need to have an understanding of satellite orbit, swaths, and revisit time, and also aerosol definition and importance for air quality. So procedures for how to ask questions. If you have questions during the training, please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go along. We will try to get to all the questions during the Q&A session that follows the webinar. The remainder of the questions that will be answered in the Q&A document, which will be posted to the training website about a week after the training. Okay, so now we're going to get into our first section on LiDAR for atmospheric sciences. I'll be providing an overview of the basics of LiDAR remote sensing, to hopefully build an understanding of how these instruments work. So first, just a quick reminder on different approaches for how we measure the atmosphere. Often we talk about in situ measurements, and this literally means you're taking a measurement of your ambient conditions, where you are in the atmosphere. So great examples of these types of instruments are thermometers, your standard meteorological instruments, as well as dropsondes, which I'm depicting here with the little weather balloon that take measurements of temperature and pressure as they fall through the atmosphere. Now, we can't always measure everywhere in the Earth that we desire, so often we use remote sensing techniques. And so these are techniques for measuring the atmosphere at distances from where we're targeting. And so ground-based radars, which I'm showing here, are a great example of this, as well as satellites, which can orbit the Earth to provide measurements at different times of day and locations. Also, we want to refresh everyone's memory on the difference between active and passive remote sensing. So active remote sensors, like the ones we'll be talking about today, these are types of instruments that emit their own energy source. In this case, LiDARs emit visible light, often from a laser, and then they measure the return signal. Passive remote sensors, on the other hand, are instruments that rely on external energy sources, such as the sun. So what exactly is the LiDAR? So first of all, LiDAR is an acronym that stands for Light Detection and Ranging. And the definition for LiDAR is an active remote sensing instrument that transmits laser light and measures the return time of backscattered light to determine the distance of an object with high precision. And most of you probably have LiDARs in your cars, for example. You often have sensors built into your car's bumpers to measure the distance between the car in front of you. Those are the things that light up when you get too close. Those are very simplified LiDARs. LiDARs are also used to map out surface vegetation and topography, like I'm showing here. So a lot of other agencies and USGS and such employ LiDAR technology to get high precision measurements of surface mapping. And while the spelling of LiDAR that I'm showing here is the technical definition, colloquially and in the literature, we use LiDAR typically in lowercase, like as in the last bullet here. So for the atmospheric sciences, LiDARs are used for various geophysical variables. That includes aerosols and clouds, which will be the primary focus of today, but they can also provide vertical measurements of winds, water vapor, gases, as well as the heights of trees and ice sheets. And these LiDAR systems can be implemented on various platforms. We'll be focusing primarily on satellites, past, current, and future satellite missions today, but they can also be deployed in ground-based systems, as shown here with this trailer. And in this case, the LiDAR system is looking up instead of down at the atmosphere. And then we also put LiDARs on various aircraft. And I'll get into the advantages of all three of these different platforms later in the presentation. So I wanted to give a quick overview of the electromagnetic range where LiDARs typically operate. They typically operate in the near infrared, the visible, and the UV. And so they span that part of the EM spectrum. And similarly, radars are active remote sensing instruments, but they transmit in the microwave region of the EM, so much longer wavelengths. And there's different advantages for measuring the atmosphere for using these different wavelengths, which I'll get into. So I wanted to go over some of the strengths of LiDARs for air quality applications. And first, I'm going to compare to what most of you probably are traditionally used to, and that's passive remote sensing of aerosols and air quality. And so for air quality applications, the strengths of LiDAR are high resolution, vertically resolved measurements, and these are on the order of meters. And in most cases, these measurements can extend from space all the way down to the surface. And in comparison, passive remote sensors typically measure the full column of aerosols, and they have very little information on the vertical location of aerosol. And as you can imagine, that's very important for air quality applications, which are interested in nose level aerosol measurements. And so if you look at these maps of aerosols, these are seasonally averaged. Yes, they depict the spatial distribution of them horizontally, but you don't have a very good sense for where they are vertically in the atmosphere. So we just discussed the advantages of using LiDAR compared to passive remote sensing. I wanted to touch on advantages of LiDAR compared to ground-based in situ measurements of air quality. And we alluded to this a little bit earlier in the presentation, but on the left here, you can see a map of surface-based EPA measurements of air quality. And you can see that some parts of the continental US are much more sparse than others, particularly in the Midwest and western parts of the country. The advantages of using a space-based LiDAR is, depending on how you construct your orbit, you can get enhanced coverage in these remote areas where you may not be able to deploy a ground-based sensor. And this not only applies to the United States, you can imagine that there are parts of the Earth as well where it'd be very challenging or just a non-starter to deploy a ground-based instrument. So how do we view LiDAR data? Unlike the passive maps that I just showed, LiDAR data is often depicted as with time on the x-axis and altitude on the y-axis. And here's an example from the CATS instrument, which I will introduce later. Along the x-axis is the latitude and longitude. It's effectively time as the satellite moved over the Earth. And on the y-axis is the altitude. And you can see in this case, the measurements extended up to 28 kilometers. And for air quality applications, we're interested in the lowest few hundred meters of the atmosphere. And in this case, I'm showing a nice smoke event that would be certainly of interest to the air quality community. So I'm going to get into the strengths of using LiDAR versus passive remote sensing. So since LiDARs generate their own energy source, you're actually able to provide measurements in the visible part of the spectrum during both day and night. And so this is a map of 1 day's worth of orbits from the Calypso satellite. And the blue parts of the orbit are measurements that were acquired during night, and the red orbits were acquired during day. So again, unlike passive remote sensors that require sunlight to do their retrievals, the advantages of LiDAR is it generates its own energy source and can provide measurements 24 hours a day. So far, we've talked about the advantages of using LiDAR data. Now we're going to talk a little bit about some of the disadvantages and things to look out for. So because LiDARs provide vertical measurements with high precision and high vertical resolution, the trade space that you lose is swath. And you can see that depicted here in this example from Calarco et al. 2014, where we have the full picture of the Mona Lisa in the top left. We have a MODIS-like sampling in image B that's been cloud cleared. We have a miser-like sampling in panel C. You can see less and less of the picture gets filled in. And then a LiDAR curtain. And you can see horizontally, at least, there's very little swath to put together the picture. So that's the trade space. We get the high resolution vertical information, but in 1 day's worth of orbit, we don't really get a whole lot of spatial coverage two-dimensionally in latitude, longitude space. Other limitations of LiDAR is they typically are only built at a few different wavelengths in the EM spectrum, and we'll touch on that a little bit later. During the daytime, the signal is plagued by solar light, and so you can see by comparing the top right curtain and the bottom curtain, which is day to night, you can see that the signal looks noisier. It almost looks like a old TV that's not getting very good signal. And so because of that noise, it makes it harder to pull out and detect tenuous features like faint aerosol, for example. Additionally, strongly absorbing features like very thick clouds or thick smoke can fully attenuate the transmitted light. And you can see that in LiDAR data here, where you can no longer see the surface beneath clouds. And when you can't see the surface, that means that the signal is attenuated. Most LiDAR systems that you'll be working with attenuate at optical depth 3. And so really thick clouds will prevent the LiDAR beam from transmitting all the way down to the surface. And so it may look like there may not be aerosol there, like in this case here. However, we just can't measure that because we're limited by the physics of the atmosphere. Now that we've gone over some of the basics of the strengths and limitations and uses of LiDAR, we're going to get into how LiDARs work. Okay, so in this section, we'll get into some of the basics of how LiDARs work. As I mentioned, LiDAR systems transmit their own energy. And so the first component of the LiDAR system is the laser transmitter. And that's what's actually generating energy and laser light that gets transmitted into the atmosphere. From there, the laser light encounters aerosols and molecules in the atmosphere, and they scatter light. Some of this light is scattered back towards the LiDAR system into a telescope, and the telescope captures this light. This is known as the receiver. And then inside the LiDAR system, there are special detectors that help measure the return signal. And so kind of colloquially, the transmitter and receiver can be in line together, like is depicted here, and that's known as the transceiver. And for a very basic but thorough overview of how LiDAR systems work, I suggest checking out McGill et al. 2003. Any reference that I've point to in this presentation will be provided at the end. So I mentioned that aerosols, clouds, molecules scatter this transmitted light. However, they do so differently. And so smaller particles, such as molecules in the atmosphere, they scatter light using Rayleigh scattering. And for Rayleigh scattering, the radius of the scatterer is typically smaller than the wavelength. And you can see that in panel A here, where Rayleigh scattering scatters light about equally in the forward and backward direction. Now, for larger particles like aerosols and clouds, they typically scatter in the Mie regime. And in this case, the radius of the particles is much larger than the wavelength. And you can see for these types of particles, they scatter much more strongly in the forward direction than they do in the backward direction. And so the way to think of this, generally speaking, is Rayleigh scattering you associate with molecules, scattering that's associated with larger particles in the atmosphere, such as aerosols and clouds. So how do LiDAR systems actually measure the vertical profiles of aerosols and clouds in the atmosphere? And so since they transmit light, we know the speed of light in the Earth's atmosphere. And what we do then is we design our instruments to look for a certain period of time so that they can accumulate any return light back from the scatterers in the atmosphere. And so that amount of time, since the speed of light is constant, equates to a distance. And that's what determines the vertical resolution of LiDAR measurements. Typically for atmospheric purposes, it's on the order of 30 to 60 meters or so. But you can design it to be coarser or finer, depending on your application. And so like a quick exercise here in the top set of bullets here is, if we have a 150 meter vertical resolution LiDAR bin, so this is a 150 meter chunk of the atmosphere. An exercise to do quickly is to determine the amount of time it takes for the LiDAR pulse to transmit back and forth to the receiver. And so if you plug in the speed of light, you should get 1 microsecond for this. And that's how fundamentally the LiDAR system works. It's accumulating signal over amount of time, and that translates to the vertical resolution that's measured in the atmosphere. And a common misconception is that LiDAR signals can only be measured, from one range bin at a time, kind of like the car example, right? For hard targets, you're actually not getting that vertical resolution. More sophisticated LiDAR systems like the one I'm depicting here, you can actually get the full vertical resolution of the atmosphere that you're interested in. So we've gone over some of the basics for how LiDAR systems operate. So the return signal that you're actually getting at range or distance is going to be a function of that vertical resolution that we just talked about, as well as the field of view. And so the field of view is kind of similar to how your eyes are looking outside of your head. You can't see very well to your left and your right, but straight ahead, you're seeing visible light. That's kind of like the field of view. And so these instruments can be designed with small fields of view and large fields of view. And so these two things combined, your vertical resolution and your receiver field of view, really depicts or determines the sampling volume that you're measuring. And I really want to highlight that it's a volume of the atmosphere that you're measuring, not a point source like in situ measurements. And so that volume is going to be representative of the average atmospheric state or aerosols or clouds in that sampling volume. Okay, we've gone over some technical details on how LiDAR systems work. Here I'm going to show you a video that I think will kind of piece a lot of this together. It'll also talk about here in the beginning how we get different wavelengths of light. Most of the LiDAR systems that I suspect you'll be working with will be 1064 nanometers near IR LiDAR systems. But those wavelengths can be doubled and tripled to get our visible and UV measurements. And so right in the beginning here, it's going to talk about this. And it's also going to talk about how these photons are measured in the atmosphere and how we can determine their altitude. So I'm going to turn the volume up here. Hopefully you can hear this just fine.
To obtain this data, CATS uses a laser that generates 3 wavelengths or colors of light. Internal to the laser, special optical crystals are used to generate these wavelengths by adding the energy of 2 photons to make a single new photon. The final output beam is made up of all 3 wavelengths, and these photons are transmitted in groups towards the atmosphere at the speed of light. As photons encounter clouds or particles, scattering of the laser beam occurs. Very few of the photons scatter directly back to the optical telescope, but the ones that return are collected and counted by sensitive detectors and electronics. By timing the difference between emission and detection, the precise altitude of the particles can be determined.
Okay, so now we've gone through some of the fundamentals of how LiDARs work. I wanted to introduce the various flavors of LiDAR that you may hear about. So the most sort of common LiDAR system that's been implemented in space for aerosols and clouds has been an elastic backscatter LiDAR. We'll get into some of those, CATS and Calypso. These are the simplest forms of LiDARs and the easiest to deploy in space. More sophisticated LiDAR systems, such as the high spectral resolution LiDAR system, or known as HSRL. These types of LiDAR systems are more sophisticated because they can separate out the molecular / Rayleigh and Me / particulate scattering. So they can separate out aerosol and cloud optical properties directly compared to elastic backscatter LiDARs. And so far, I've shown a few examples of that, CATS and Calypso being backscatter LiDARs. And then we also have HSRL LiDARs as well that provide similar sorts of measurements. Doppler wind LiDARs. So these are LiDAR systems that actually use Doppler shift measurements of Rayleigh and Me scatterers to determine horizontal and in some cases vertical winds. This is an example from an airborne instrument called Dawn that's flown for NASA on numerous field campaigns. There are Raman LiDARs and differential absorption LiDARs. These are primarily designed for water vapor and trace gas measurements. And here's an example of one of the differential absorption or dial LiDARs that are used to provide vertical measurements of water vapor. And by differential absorption, they're channeling different wavelengths and using the ratio of different wavelengths to determine how much water vapor, in this case, is in the atmosphere. And then similarly, we have trace gas measurements. This is an example of ozone profiles. These were acquired from the ground. And they use similar techniques as I just went through for the water vapor example from HALO. And then finally, I mentioned that LiDAR systems are used for topographic measurements. And so for earth sciences, atmospheric sciences, and cryospheric sciences, these are highly precise, high vertical resolution measurements that are trying to measure things such as tree canopy height here. This is an example from the JEDI LiDAR system that was on the space station. And then there's some additional LiDAR systems that I'll be talking about later that have been targeting measurements of ice sheets and glaciers and such, and they're changed with time. Okay, early on I mentioned that LiDARs can be deployed on various platforms. I want to talk about ground-based LiDARs first, their advantages and their disadvantages. And so one of the big advantages of ground-based LiDARs is they can measure continuously from a fixed point. So this is really advantageous for taking measurements of the diurnal evolution of the atmosphere. So how clouds evolve, how aerosols evolve, gases, the planetary boundary layer. How do these change throughout the day? You know, when you have a fixed point measurement, this measurement approach is very advantageous. They also, since they're on the ground, they're not as limited by power as airborne and spaceborne implementations. So they can really dial up the laser energy. And so you can get really good signal to noise from the ground. And then additionally, since you're on the ground, you can pair these instruments with other meteorological instruments such as radars, radiosondes and such to establish super sites, depending on the science application that you're into. And so an example of this is the DOE's Southern Great Plains super site that has all sorts of instrumentation, including LiDARs, to measure the atmosphere. All right, so moving on to airborne LiDARs. So these are advantageous because it allows you to really go after atmospheric processes that evolve quickly over time. You're thinking about convection, smoke plumes, you want to measure these, several passes over these. And there may be spatial variability that you'd like to sample as well, which you cannot do from the ground. The other advantage of using airborne LiDAR systems is, again, you can add additional instrumentation to the payload depending on your science. So you can put radar instrumentation, passive remote sensing, all to piece together sort of the science story that you're after. And in this case here, I'm showing the NASA ER2, and you can see this is the cloud physics LiDAR installed in one of the superpods here. And this LiDAR system operates out of the window in the forebody of the aircraft. And you can see there's other pods here, there's other instrumentation installed in the aircraft, and this can change depending on the science that's targeted by the airborne mission. All right, moving on to Spaceborne LiDAR. First, we want to talk about some of the different orbits and orbital strategies that Spaceborne LiDARs have used. To date, all Spaceborne LiDARs for Earth science have been launched in a low Earth orbit. And that reason is when you're actively transmitting laser energy, you actually want to be as close to the Earth's surface as you can. The further you go away from the Earth's surface, the more energy you have to transmit, and the worse your signal to noise is. And so for that reason, there haven't been any geostationary LiDAR implementations, used by NOAA, for example. Now, for depending on the science, different types of low Earth orbits have been employed. Probably the most common to date has been a polar orbit. So the advantage here is you can see most of the whole globe, but you're only sampling once per day. And these orbits may be either sun synchronous, so there's the equator passing time is the same every day, or they can precess, which means that equator pass time changes day to day. There are also low inclination orbits, and so the trade space here is while you may not measure the entire globe, you're getting diurnal measurements throughout the day at a higher frequency than a precessing polar orbit, for example. So depending on your science, these two different types of orbits can be employed for LiDAR remote sensing from space. Okay, I've mentioned signal to noise ratio a little bit so far. And so the accuracy with which a LiDAR can derive its spatial and optical properties depends on its signal to noise. And as I mentioned, this depends on several things. The field of view, so essentially how large your telescope is, the distance between the instrument and your target, the amount of energy you transmit. And because of this, which I alluded to in the previous slide, the signal to noise of space-based LiDARs is lower than ground-based and airborne LiDARs because it's so much further away from the targets of interest. And often spaceborne power requirements are such that you can't transmit the same amount of power that you can from ground or airborne. And so signal to noise ratio during the daytime, as I previously mentioned, is always lower because you have solar light that the LiDAR system is measuring. And again, this makes it more challenging to detect aerosols and clouds because your signal to noise is lower. And so on the right here, I'm sort of showing both of these things at the same time. So this is an airborne underpass of the cloud physics LiDAR from the ER2 that I showed on the previous slide compared to Calypso from space. And you can see, yes, the SNR in the airborne curtain is much higher. And that's because the aircraft is flying at a much lower altitude. And then during the day here, you can see that some of the fainter features that you're seeing in the airborne data, this is some faint aerosol here, this is some faint clouds here. it's really challenging to see that by eye from space. And so to account for this, traditionally algorithms will average the signal over longer horizontal distances to be able to pull out these fainter features. Okay, so moving on to section 3, I wanted to provide an overview of LiDARs in space. And so I'll be talking about past, current, and future LiDAR missions. And what I hope you really pick up on is that LiDARs in space are very rare, and they're relatively new compared to a lot of sensors that have been put in space. So I'll step through these, and hopefully at the end you'll be excited about some of the upcoming LiDAR missions that are planned for the future. Okay, so starting with the past LiDAR missions. So the very first Spaceborne demonstration of LiDAR is called the LIGHT mission. And this was done in 1994. And I find this fascinating. This was a LiDAR system that was put on the space shuttle. And you can see it in the left here. The space shuttle was actually flown upside down, and the LiDAR system was facing the Earth here in this direction. And it flew for 53 hours. And that may not sound like a whole lot, but it really laid the groundwork and was a pathway for some of the more famous LiDAR systems that followed this. But this LiDAR system was critical in unraveling some of the things that we didn't know at the time. For example, the altitude from which Saharan dust was getting transported from the Sahara into the Caribbean. In this time frame, these 53 hours, there were several dust case studies that LIGHT was able to measure. And so this really served as the groundwork for free-flying spaceborne LiDAR missions that would follow. Okay, I mentioned that LIGHT was the first spaceborne LiDAR that flew on the space shuttle. ARSET, which launched in 2003, was the first LiDAR that flew as a free flyer in space. Now, ARSET was designed as an altimeter to measure ice sheet elevation, but you can see from this curtain, it actually provided measurements of aerosols and clouds as well. So it's the first demonstration of a free-flying atmospheric measurement or LiDAR-based measurement, and that was in 2003. And again, this, similarly to LIGHT, laid the groundwork for future atmospheric-focused LiDAR missions. Moving on to Calypso, I think you've heard me talk about Calypso. You probably have heard about Calypso. So in 2006, NASA and Kinéis partnered to develop Calypso. And this was the first LiDAR for space that was designed for aerosol and cloud remote sensing. This LiDAR provided measurements at 2 wavelengths, at 532 in the visible, 1064 in the near IR. And this operated from 2006 to 2023. So almost 20 years of operation, which is phenomenal for a LiDAR in space. And so the data record for Calypso is fantastic. It flew as part of the NASA A-Train. So you have yearly co-located measurements with CloudSat, Modus Aqua. And it really was one of the highlights of what was known as the Earth observing system period. Now, following Calypso, the CATS LiDAR was built as a technology demonstration, and that was meant to fly and did fly on the International Space Station from 2015 to 2017. CATS provided very similar measurements to Calypso, similar wavelengths. However, because it was on the ISS, which orbits between the latitude range of plus and minus 52 degrees, it was a precessing orbit. So the advantage of CATS was you were able to get measurements at different times of day, again, at the sacrifice of global coverage, which Calypso provided. More recently, in 2018, the European Space Agency launched the Aeolus LiDAR. And so I mentioned that Doppler wind LiDARs rely on using aerosols and clouds, as well as molecules in the atmosphere to determine wind speeds. And so while not designed specifically for aerosol and cloud remote sensing, AOLIS provided those data products and was a nice complement to Calypso until it also ceased operations in 2023. Okay, so what's going on in space now for LiDAR? We currently have the follow-on to ICESat, ICESat 2. And so this has been in space since 2018. It was a 3 to 5 year planned mission, so it's met its mission requirements. And similar to ICESat 1, it's primarily a topographic altimetry mission. However, it provides vertically resolved measurements of aerosols and clouds at 532 nanometers. An example of a profile is here, and you can see clearly, while the primary measurement for ICESat 2 is the altitude at the surface and ice sheets, you can see various atmospheric features that the instrument provides. Clouds over the UK, some aerosols over France and Spain, and then the topography that the mission is primarily interested in over the Atlas Mountains. Now, very recently, ESA has launched the EarthCare mission, and this is an exciting mission. This is the first atmospheric and cloud LiDAR that's using the HSRL capability that I previously mentioned. This is done at 355 nanometers, so this is out of the near IR, visible, and into the UV. And this launched last year from Vandenberg Space Force Base. And in addition to the 355 nanometer UV LiDAR, HSRL, known as ATLID, there's additional instrumentation on the payload, which includes a CPR W-band radar, a multispectral imager, and a broadband radiometer. So EarthCare is really targeting the Earth's radiation balance and how it's impacted by clouds and aerosols. And as I mentioned, that launched last year. The mission is still up there in space, and data is now publicly available to the public. So if interested, you can download and start to analyze EarthCare data. An example of some of the preliminary data is shown here, and you can see this is similar sort of scene compared to some of the CATS and Calypso curtains that I showed. Here we have a mix of cirrus clouds up at around 18 kilometers. You can see some deep convection. Again, as I mentioned, when you can't see the surface, the signal is attenuated, so we don't actually know what's going on here because the clouds are so thick. And then you can see some aerosols. So we have some desert dust, some marine aerosol over the ocean. And again, these data are coming online, and I really want to thank my colleagues at ESA, Fabian Mornay and Thorsten Fair, for providing these slides to us. And I should mention that this is also a partnership with JAXA on the radar side as well, not just ESA alone. Okay, so what's in store for the future? So the first AOLIS wind LiDAR that I spoke about was a technology demonstration. And so following that, EUMETSAT, which is similar to NOAA here in the United States, and ESA have partnered to develop another version of AOLIS known as EPS AOLIS. And this one's going to be operational, so assimilated into data assimilation models. And this is slated to launch in the 2030s. And so based on their experience with the first AOLIS, they've made design changes to improve the horizontal and vertical resolution, improve signal to noise ratio, data latency. This is really geared towards the data assimilation side of the house. And then they've also decided to include some design changes that help discriminate aerosols and clouds better, which I'll discuss more about how that's done in part 2 of this training. Also coming up from the US side in partnership with the Italian Space Agency is Luce. And so this is going to be Raman LiDAR that's going to fly as part of the NASA Atmospheric Observing System. And that's slated to be a polar orbiting LiDAR. This is very early in the game here, but at the moment, the plan is to include UV, visible, and near IR wavelengths. As I mentioned, it's very early on and designs being finalized, but we're very excited about this potentially exciting mission in the early 2030s. Okay, so getting to the summary of part one. First of all, I want to say thank you for attending part one of this. And I wanted to highlight some of the topics covered today and key takeaways. And so hopefully following this, you're able to recognize the capabilities of LiDAR active remote sensing and measuring vertical profiles of aerosols and clouds, and for informing air quality applications. Some of the key takeaways I have bulleted there that I hope you will walk away with. And that is the power of active remote sensing for vertically profiling and air quality applications, a basic understanding of how LiDAR systems work, the various implementations of LiDAR, meaning ground, air, and space, and the limitations of each, and then an overview of past, current, and future LiDAR missions. Another key takeaway is I hope you recognize the strengths and limitations of LiDAR observations, strengths being the high resolution vertical resolution not possible from other passive sensors, as well as near surface observations, right? So the LiDARs provide vertical information for where aerosols are, where passive sensors can struggle. However, there's nothing free. The limitations are LiDAR swath, and you can be impacted by poor daytime signal noise and signal attenuation in very thick clouds and smoke plumes like we showed examples of. So looking ahead to part two, the goals there will be to interpret information from LiDAR measurements to understand how we get from measuring raw photons to discriminating cloud phase, aerosol type, and optical properties. So going from what we call level 0 data products to level 2 data products. And then we're going to go through how to access data from some of these Spaceborne campaigns that we discussed, and we'll walk through a few case studies to check the understanding of going from these level 0 measurements all the way to level 2 data products. So we'll have some examples of that to work through. And again, we'll walk through how to access and download data from these various Spaceborne LiDAR missions. Okay, so just a few notes on the homework. There will be one homework assignment that will open up following part 2 of our training. That can be accessed on the training web page, and the answers to the homework will be submitted via Google Forms. The homework will be due June 25th, and then following completion of both live webinars and the homework assignment, you'll receive a certificate via email about 2 months after completion of the course. Okay, so if you'd like to get in touch with me, my contact information is there. We also encourage you to check out the ARSET website, as well as check out the ARSET YouTube channel. And we also encourage everyone to check out our sister program, Develop. Again, I promised I'd provide resources for some of the papers, as well as some of the websites that I was showing data from. Those are all provided here. Again, if you have any specific questions about any of this, feel free to reach out using my email address from the previous slide. And now I'll take any questions from the audience. So the first one, when a LiDAR is ground-based, what types of measurements can be done upwards? And so the answer there is you can do the exact same types of measurements from ground-based systems as airborne and space-based systems. The big difference is that ground-based systems are looking upwards and they are static in terms of their location. So you can get a time series of atmospheric constituents using the ground-based systems. We talked a little bit about attenuation. So when looking up as opposed to looking down, ground-based LiDAR systems can get attenuated looking upwards. So if there's a really thick cloud deck above the ground-based system, for example, you may not be able to see higher parts of the atmosphere. Just like the opposite was true from space-based and airborne systems, where if there's too much attenuation, you'd be unable to see the surface. Okay, a question about JEDI. And so, yes, yeah, JEDI is a LiDAR mission that's operating on the space station now. We discussed that a little bit as a type of LiDAR. It's referred to as an altimeter. But that instrument really has very, very limited information or limited capability to measure atmospheric constituents. It's really targeting tree canopy heights. So not so suitable for aerosol and cloud measurements that we're focusing on here. What type of applications on clouds can be made using data from EarthCare? So EarthCare is very exciting because it has, as I mentioned, several types of instruments on the platform. So the LiDAR is just a piece of it, and that's going to provide measurements of thin cirrus clouds, but the really thick clouds, like in the example that I showed where there was thick convection, those will be impacted by attenuation. Now, when that happens, the beauty of the EarthCare payload is you can use the radar that I mentioned to fill in cloud measurements below profiles where the LiDAR is attenuated. So you can think of EarthCare as a more sophisticated version of Calypso and CloudSat if you've worked with that data before. It also has the imager that I mentioned, so you have some passive swath information there, and you also have some broadband radiometer measurements. So that payload's really well suited to go after understanding aerosols, clouds, and radiation and their impacts between the three of them. Let's see, can I use LiDAR images to monitor subsidence of underground mines? I have not heard of that type of application for LiDAR data, but I can research that offline here a bit more and hopefully get you a more thorough or concrete answer. Okay. Is there any priorly predicted value of distance dealing with future advanced LiDAR mission? Maybe I could speak to that real quick in case that's what they're after. So for Aeolus, the EPS Aeolus that's a partnership between ESA and EUMETSAT. And so the goal there is to build a series of Aeolus wind LiDARs to be operational as part of the EUMETSAT suite. So the first Aeolus was just a demonstrator, so there was not a partnership with EUMETSAT there. And they're moving towards, and they really would be the first to do this, operational LiDAR measurements of winds to be assimilated into their forecast models. All right, where can I download information from the Amazon forest to analyze water vapor, gases, and vegetation canopy? So if you're interested in JEDI, for example, that information is publicly available. I have to confess I work very little with JEDI, but we will confirm that typically NASA will put their data on what's called a DAC, data repository, and so we can track down which one houses JEDI data for download. I suspect imagery is most likely on their website. That's pretty common for LiDAR groups to do their quick looks on their website, But if you want to do download volumes of data for quantitative analysis, the DAC is probably better suited for that. How difficult is it to implement HSRL in comparison to conventional elastic backscatter LiDAR? So that's been done now by ESA, so Aeolus and EarthCare both have demonstrated the HSRL capability. It's just a bit more sophisticated system, and so yeah, there's been tons of airborne demonstrations and ground-based demonstrations of HSRL. It's again a more sophisticated system, which traditionally has proven to be more challenging to get it in space, but both Aeolus and EarthCare have demonstrated that now. Can we reduce the power usage by limiting noise transmission using machine learning algorithms? Yes, and so there's lots of groups that are working on signal denoising during daytime conditions. I believe I speak a little bit to that in part 2, so tune in next week. But yes, there's lots of groups leveraging machine learning for signal denoising to improve SNR. Okay, it would be nice to have practical example of measuring aerosol plume height and a few other types of applications. So we'll get into this next time. So please come back next week to learn how to interpret the curtains and plume height and where to access quick looks and such. What is the rough cost for a ground-based system? That's a good question. And I'll have to get back to you on that one. That's going to vary quite a bit by the type of system. So a elastic backscatter LiDAR system, such as MPLNet, those are going to be more affordable than more sophisticated LiDAR systems, such as perhaps HSRL or an ozone LiDAR. It's going to be kind of system and target dependent. Okay, your cross sections of the atmosphere were an excellent communication tool, but you also showed how they're useful for assessing signal to noise quality. Will you cover signal to noise and its relationship with how to identify atmospheric features in the next? Yep, absolutely. So we'll walk through all of the feature detection or the theory behind feature detection and show some real world examples. And we'll touch base again on how the daytime signal, at least traditionally, before these machine learning algorithms that I just mentioned have been incorporated, how that's accounted for and dealt with in these in the feature detection algorithms. How efficient is LiDAR for measurements of PM10 aerosols? Is there any better remote sensing technique as compared to LiDAR for measuring PM10? So LiDAR doesn't directly measure mass concentration of aerosols. There are certain wavelengths that are going to be better suited for PM10. So the near IR wavelength, 1064 nanometers, it's going to be better suited for PM10 than PM2.5, whereas the visible and the UV will be better suited for that. And again, remember, you're measuring a volume. So thinking of the LiDAR grid box closest to the surface, that's a volume that's typically several hundred meters horizontally by 30 to 60 meters vertically. So LiDARs don't directly measure that, but they give you a sense for the concentration based on the backscattered signal. Okay, for my master's thesis, I'm working on mangroves in Cameroon. One of the goals is to compute canopy height. I had to look at JEDI, but as the samples are spaced enough, can the output be really informative using these data for machine learning? Yeah, so for this, I would revisit the JEDI website again. I'm not an expert with the JEDI instrument. I apologize for that. But perhaps we can get some follow-up, a follow-up response to this following this session. Okay, it looks like number 15 looks like someone is using drone for mining subsidence. So thank you for whoever submitted that. Can dial LiDAR be used to measure NO2 concentrations? Yes, I believe some groups are measuring NO2 here at Goddard. And similar to ozone and water vapor, you can get the vertical resolution of these constituents. Okay, number 17 is asking about the wavelength for, so it's 355 nanometers is the wavelength of the laser transmitter. So that's the laser beam is being transmitted at 355 nanometers. Like I mentioned, for atmospheric science applications, they're typically the wavelengths are 1064. That wavelength is doubled to 532 to get green light, and then it can be tripled to get 355 UV light. And the reason 355 was chosen as opposed to 532 for the HSRL technique is at 355 nanometers, you get a lot more backscattered signal from the molecules in the atmosphere. And so if you recall, HSRL systems separate the molecular and the particulate signals. And so if you have a much stronger molecular signal, you can make that separation easier. Okay. What are some examples of use cases covered by ground-based LiDAR which cannot be served by Doppler radars? So radar systems are going to be measuring longer wavelengths in the atmosphere. And that basically translates to they're going to be sensitive to larger particles. So hydrometeors, raindrops, snow, things like that. That's going to fully attend the LiDAR system. So what LiDAR can do that radar cannot is measure very thin clouds like cirrus, or for these really thick systems, just to get the cloud tops before they attenuate. And so I always like to think of LiDAR and radar as kind of like filling in the column, right? So the radar is not sensitive to certain parts of the atmosphere where the LiDAR is, and the opposite is true for the LiDAR. It'll attenuate for these larger hydrometeors. And so just one more point there. So that's why a lot of times we'll see these super sites like the Southern Great Plains where they'll put a LiDAR and radar together so that you can piece together the full column. Okay, so how is LiDAR data efficiently useful for monsoon prediction? So it can be used to provide a real-time measurement of, I'm thinking Spaceborne LiDAR here, cloud top height. And for the same reason I just mentioned, if the LiDAR goes over a precipitating system, it can give you a measurement of that height. The LiDAR itself is not going to predict anything going forward, but that information can be used to provide valuable information to our forecast models to predict, weather systems in real time. LiDARs are not useful for predicting longer term, monthly scale, seasonal scale atmospheric phenomenon. It's a snapshot, and that information can be used to constrain forecast models for a few days, perhaps. How can LiDAR be applied to precision agriculture, if at all? That's a bit out of my realm. I think of the altimeters for this, canopy height. I, can think of other useful types of measurements outside of LiDAR that might be better suited for this, but we'll look into this. Can LiDAR measurements at different wavelengths detect the absorption properties of brown carbon in the atmosphere? Yes, so that's so when we have LiDAR systems that have multiple wavelengths, typically in the UV and the visible, they will do a calculation called the angstrom exponent. And so they'll take the ratio of those two wavelengths, and that information can be used to assess the particle absorption in this case. So it helps inform what we think that aerosol is. So multi-wavelength LiDARs in the UV and visible especially can do that, use that information to assess aerosol type. We'll get into how particle shape measurements from LiDAR can also inform that next time as well.
If there are no questions, we can probably close for today. So just to remind everybody, all the homework, all the videos, slides, everything for today's training is on the training webpage. The homework will be available after part 2 next week. I see a lot of questions about that in the chat. So just to remind everybody, and thank you so much, Ed.
Oh, thank you. I really enjoyed this, and I look forward to part 2 next week. Thank you, everyone.